So let's take a look now at example 3 and see another scenario here where we're going to try to optimize something. I want to try to find in this question a point that's on the parabola y squared is equal to 2x that ends up being closest to the point 1, 4. Now, one of the things that we'll notice right away is that if we were to try to sketch a graph of this particular parabola, it's going to be a little bit difficult because this is a parabola that has the shape of 1/2 y squared. So it's x equals 1/2 y squared, meaning it's a parabola that opens sideways. Now we could easily go ahead and just kind of eyeball roughly what this is going to look like. If it opens to the side, it's going to be some sort of a parabola that looks like this. And I know that there are lots of points that are on this particular curve. I'll also notice that the point 1, 4 is certainly not on the curve. Notice if I plug 4 in for the value of y, I'm going to get 16 times 1/2. That's going to be 8. So the point 8, 4 is on my parabola, but not the point 1, 4. Let's suppose right now that the point 1, 4 is like right here. Okay, this is 1, 4. And I'm interested in looking at all of the different points that could ever be on this particular parabola and trying to think ultimately about, well, which point on the parabola is this point closest to? Well, I could probably start to imagine that I could draw maybe to this point. There's a distance that I could sketch. Or maybe over here, there's a distance that I could sketch. But are those the shortest possible distances? To go ahead and actually create the shortest possible distances, or the shortest possible distance, I'd probably want to go ahead and draw a straight line right here to some point on the curve, which is going to have coordinates x, y, like mystery coordinates. I don't know what they are. But I can tell immediately that what I'm interested in trying to minimize, if I want to find the closest point, is I'm trying to minimize a distance that we'll call little d. Okay, so let's see here. I want to try to find this distance little d. I want to make it as small as possible. So where do I have to move this point to make that happen? Okay, so I'm going to go ahead and start again by writing out what I want to maximize or minimize. So we want to minimize little d. That is the distance from 1, 4 to the parabola. Okay, now, to do this, it would be great if I could go ahead and think about minimizing a distance. Okay, wait, I have a formula for distance between 2 points. I could use a distance formula. So I could say d is actually going to be equal to, and I know how the distance formula works. It's really just a rework of the Pythagorean theorem. I'm going to take something like x minus 1 squared plus y minus 4 squared, and there's my distance formula. Notice if I was to just square both sides, this actually looks exactly like, again, Pythagorean theorem. And you can see where Pythagorean theorem comes in here by just taking a look at the corresponding triangle that I could have sketched right here. Notice that this point right here would have had an x-coordinate of 1, but a y-coordinate of y. And then when I go ahead and actually measure the lengths of my different sides, it's really easy to go ahead and arrive at these quantities. So I could go ahead right now and I could actually calculate d prime as long as it was possible to get this equation in terms of one variable. So let's go ahead and actually do this. I'll start by saying we see that d could be rewritten as, and notice, I actually have a perfect way to make a substitution right now. In place of x, I could just put 1/2 y squared. So 1/2 y squared minus 1 plus y minus 4 squared. So I have a formula now with one variable. I'd be ready to take the derivative. The issue right now is that this derivative is actually going to be really messy. You could probably see how complicated it's going to be to compute. But notice what would happen if I was to go ahead and instead square again both sides. If I was to do this, I can see something that's going to be much, much nicer. First off, this right-hand side is going to be a way easier derivative to compute. And over here on this side, I'll notice something. I no longer just have this distance d, but I have that distance squared. But here's something that's kind of important. Whatever value I find that minimizes a distance, It's going to be, so like whatever value of y is going to make d as small as possible is also going to be the value of y that makes d squared as small as possible, right? Like if my smallest distance, right, like so let's say I had possible small distances, 1, 2, or 3, right? And I look at all these possible values of d. Maybe d could be any one of these. Well then, which one of these is going to have the smallest square? Well, if I look at the squares of all these values, notice that the smallest d value also has the smallest squared value. So what we're going to do here instead is we're going to go ahead and replace this d squared, and I'm just going to replace that with capital D. So imagine that capital D is d squared. In fact, I'll put that here on the side. Note, little d, we're just going to, or little d squared, we're just going to call equal to big D. So what I'm going to do now is I'm actually just going to go ahead and take the derivative of this. I'll find what minimizes d squared, but that will be exactly what minimizes the value of d. So I'll start by saying now that we calculate d prime. Here I'm going to have to start by using my chain rule. So 2 times a 1/2 y squared minus 1 to the first. Then chain rule is just going to get me a times y, because it's going to be 2 times a half y to the first. Over here, I'm going to get 2 times a y minus 4, and my chain rule is just going to give me a times 1. So if I was to simplify this out a little bit, notice here I can distribute my value of 2 as well as a value of y, and I'm going to end up with y to the third minus 2y plus 2y minus 4. That comes from over here. So I can simplify this down to actually just be y to the third minus 4. So I need to figure out when this is going to be equal to 0 and when it's going to be undefined. So I'll say that d prime is going to be equal to 0, well, when y to the third minus 4 is equal to 0, which is of course whenever y to the third, oh, sorry, not minus 4, this should be minus 8. My apologies. Minus 8. So whenever y to the third minus 8 is equal to 0, which is whenever y to the third is equal to 8, which is of course whenever y is equal to the value of 2. I can also see here that d prime is never undefined. So this right here is my only critical value. So maybe this corresponds to a minimum, but maybe it corresponds to a maximum. This is just a potential candidate. It might not even correspond to anything. So let's go ahead and draw out our number line here and think about if I have a value of 2 for my value of y, then what does my value of d actually end up as? Or sorry, d prime. Well, let's see. I have a little formula here that's just y to the third minus 8. So let's suppose that I plug in a value like a 3. Well, that would give me 3 to the third. That's like 27 minus 8, and that's positive. If I plug in a value like a 1, I'm going to get a negative. And so I can see here that I'm going to have a minimum value, but since it's the only value there, it's the absolute minimum value. So this is great. I can now go ahead and see that the value of d is minimized when y is equal to 2. So the value of little d is minimized when y is equal to 2. That's also going to work. But of course, if that happens to be true, then if I know the value of y, and the question says that, the value of y where this is going to be smallest is going to have a y coordinate of 2, then I should be able to find the x coordinate, no problem. In fact, I even have a formula right here that tells me if I have a y, how to compute my value of x. So I'm going to go ahead and actually do that here. I'll then be able to say if y is equal to 2, then x is equal to 1/2 times 2 squared, which notice also produces 2. So I can reach the conclusion that the point on y squared equals 2x that is closest to the point 1, 4 is the point 2, 2. I found it. 2 for the x, 2 for the y. So whenever we're dealing with distances and trying to maximize or minimize distances, we can see again that we could set up a distance formula. But since the distance formula is annoying to compute a derivative of, because it's going to require that you do a lot of complicated chain rules, you're going to have a 1/2 brought down to the front and then a negative 1/2 power left over. That's going to produce negative exponents, meaning you're going to have really complicated looking derivatives with square roots in the bottom of fractions. It's going to be a mess. Since that happens with the derivative of a distance formula, notice here that instead we're going ahead and looking at what is going to be d squared and trying to minimize that as well. And like we said at the end, since the value of d squared, or what we called capital D, is minimized at a value, the value of little d would also be minimized at the same value. And so whenever you're working through, like, say, worksheet problems or exam questions, and you come across questions like this where you're dealing with a distance, try to always, instead of focusing just on d, focus on capital D, or what we said was d squared. It'll make your life a lot easier.